SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process from our great Prime Minister, late Lal Bahadur Shastri, who says success in science and scientific work come not through the provision of unlimited or big resources, but in the wise and careful selection of the problems and objectives. Above all, what is required is hard, sustained work and dedication. This is a very interesting and thought provoking statement to be pondered about, particularly by the researchers. And if we want to do good research, we must think about this statement and also act on it. Let us recall what we learned in the last lecture. In the last lecture, we discussed about the solid propellant and various kinds of solid propellants like composite propellant, homogeneous propellant, and your nitramine propellant and composite modified double base propellant. And also we looked at composition and its ingredients and how those ingredients plays a very important role. And then we also looked at how to manufacture the double base propellant in a very succinct manner. Today we will be discussing about composite propellant, which is being very much used profusely due to its several advantages over the double base propellant, because it will be having higher burning rates and also it is quite stable in nature. As you go along, we will see some of the advantages about this composite propellant over the double base propellant in later lecture. So, composite propellant, as the name indicates, it will be containing fuel, oxidizer and ingredients in retaining their physical identity. That means its shape and size will be there, but it will be compact, but it is not that mixed at the molecular level like double base propellant. Rather, there will be interface between the fuel and the oxidizer and other ingredients. So, the most commonly fuels which are used in the composite propellant are two, which is one of them is STPB and which is known as hydroxyl terminated polybutadiene. You can see that this is your chemical formula. It is basically a long chain, straight chain, it containing carbon, hydrogen and oxygen. And it is being used very much because of fact that it can be loaded well with the metal powders to enhance the its burning rate. And beside this, it is quite cheap and available easily, and then its molecular weight also is quite being the longer chain. So, similarly CTPB, the carbonyl terminated polybutadiene, which is also used, and however, in India STPB is being used very much in several applications like a missile application, spacecraft and other things related to the rocket engines. And there are several synthetic polymers are being developed which can be used as a fuel in the composite propellant, and some of them are polysulfide, polyester, epoxy, polyurethane, polyxylogen, polybutadiene, polyamide, polyethylene, polystyrene and phenolic or the cellular resin. If you look at polyethylene and polystyrene and polybutadiene, we do use in our civilian applications and several of them, and these are of course used as a propellant. Beside this, several metal powders are being used as a fuel. Some of them are aluminums, magnesiums, boron, metal hydrates. And these are used as a fuel, as I mentioned, because so that its burning rate of the propellant can be increased easily. Beside this, it will make it compact, so that more amount of propellant can be stored in a smaller volume. Of course, its density will be increased, that is the one disadvantage you can say, but however it is being used. If you look at the aluminums and boron and even metal hydrates have low molecular weights, therefore, they are being preferred over other metal powders in the composite propellant, as the molecular weight will be lower, then the products is likely to be also, the product gas molecular weight is likely to be lower. Hence, there will be increase in ISP, or the specific impulse. Let us look at now some of the oxidizer, and there are several kinds of oxidizer, but 5 of them are being shown in this table, which are being commonly used, and most popular among all these oxidizer is ammonium perchlorate, and this is basically is also known as AP in short form, and because of this is being profusely used, and it is having a moderate performance, and it is decomposed easily, and it is quite stable in nature, and its cost is also moderate, and it gives around 59.5 percentage of oxygen. Of course, its density is something 1950 kg per meter cube. It is little lower as compared to potassium perchlorate, and potassium perchlorate density is 2520, and if you look at density is higher, that means more amount of the propellant can be stored in a very small zone, so that it will be more compact. Unfortunately, potassium perchlorate will be having 46.2 percentage of oxygen. So, therefore, that way it is ammonium perchlorate is advantageous. Potassium perchlorate will be having also moderate performance and low regression rate, whereas the ammonium perchlorate will be having little higher regression, that depends on the kind of fuel being used. And this potassium perchlorate short name is also known as KP. And another important this is which is used as a basically ammonium nitrate, and which can provide 60 percentage of oxygen, but however, this temperature is very low. As a result, its performance will not be that good, and it is of course moderately cost, its cost is moderate, and this is generally used as a gas generators, because it is will be producing a lot of gases, and when you add little bit HMX, and it will not give you the smoke, but it will produce a lot of gases. So, that is also advantageous with this ammonium nitrate, which is known as AN, and potassium nitrate is having 47.5 percent of oxygen, and its density is 2110. It is higher than the ammonium nitrate, which is around 1730, and it is having a low performance, and its cost is also low. And nitronium perchlorate, which is very easily decomposed, and it is of course having highest percentage of oxygen, and it is having also the density of 2200. It is very reactive and unstable, therefore, it is not being used very much unless otherwise special need is required to be used this kind of propellants. So, we will be, as you go along, we will be discussing about more some of them in detail. And if you look at in First World War, this trinitrotoluene is used as an explosive, which was very much properly used, and therefore, people consider the extent of explosiveness as in terms of TNT. But later on, more exotic explosive are being developed and used. One of them is RDX, it is known as cyclotrimethylene trinitramine. its formula is given here. And the other one which is also very popular as compared to TNT, that is HMX, cyclotetraethylene tetranitramine, and these are two explosive can be added to the propellant such that its regression rate will be improved, so also the performance of the rocket engine. Beside this, the smoke can be reduced from the propellant, which particularly can be used for military application, such that radar cannot detect the missile firing. And some of the fuel we will be now discussing, and these are given in this table. The acronym or this basically PU is stand for polyurethane, and this fuel is used in Polaris rocket engine, and CTPV, as I told you, this is a carboxy terminated polybutadiene, which is used in Munitimon in stage 2 and 3. And STPB is stands for hydroxy terminated polybutadiene, which is used profusely by a lot of countries due to its higher solid loading, as I told, and it is being used in our spacecraft like PSLV, GSLV, and also some of the missiles. And in India, it is really the workhorse for providing for making the composite propellant. And PVAN is polybutadiene acrylonitrile, and which is was used in Titan and Shuttle and engine, and PNC is plasticized nitrocellulose, which was used in Minuteman and Polaris space vehicles, and GAP is Gilcedal azide polymer, which is used as an energetic binder. So, if you look at sometimes we use fuel and sometimes we use binder, because of fact that most of the fuel are basically polymer, which are used to provide structural stability and also act as a fuel, because it will be containing the carbon and hydrogen and also some oxygen to some extent. And as it is a polymer, it will be having a long chain and which can be cross linked, such that during the curing process, and this will make the other like crystal like oxidizer like ammonium perchlorate, ammonium nitrate, these are all crystalline, and to also ingredients to bond them properly or compact them, so that also it can take the impact load, so that the grain cannot be disintegrated during its operation, particularly when subjected to high acceleration. However, this fuel the binder must be processed well during mixing, casting and curing. This has to be done in a proper manner, so that its structural stability can be retained, and also it will be mixed properly. It must maintain the integrity of solvent under the loads, storage, temperatures, and stay bonded to particle, because that is why this is the fuel is known as a binder. This is a very important utility of the fuel. It will not only act as a fuel, but it will act as a binder. Generally, minimum amount of fuel is preferred, as the oxidizer contains limited amount of oxygen, as we had discussed earlier, that it is not 100% oxygen. Therefore, the quantity of the fuel used is less in case of composite propellant. Conventional composite propellant usually contains between 60 to 72% of AP, up to 22% of aluminum as a metal fuel or any other metal as a matter of fact, and 8 to 16% of binder fuel, including its plastic. Sometimes people may use more than that, because of fact that the composition varies from companies to company and also the organization to organization. So, therefore, they do experiment and find out what is the best suitable for their application. Let us look at typical composite propellant in this table, and ammonium perchlorate is 70% by weight of ammonium perchlorate is used, and which will function as an oxidizer, and polybutadiene acrylonitrile known as the PVN is used as a fuel or binder, you can note that its percentage is only 11.8% and aluminum powder in this composite propellant is 16%, which act as a fuel, and epoxy, which is used as a curing agent, is around something 2.2 percentage by weight. This is quite low. So, with this propellant, if you cast it and then use in a thing, and also you can really calculate like what will be the density. Density will be 1760 kg per meter cube, and the theoretical temperature Tc 3392 Kelvin, and this is the theoretical calculation. Characteristic velocity will be getting 1568 meter per second, provided the chamber pressure is 700 megapascals. So, of course, you know that chamber pressure does not affect much the temperature nor the characteristic velocity. However, it will be affecting to certain extent. So, let us look at a typical composite modified double base propellant. In this case 20.4 percentage of ammonium perchlorate is used as an oxidizer, and whereas the 21 percentage of the aluminum powder is being used which as a fuel. And apart from this, we use also the nitrocellulose as a binder, and whose percentage is quite high. If you can look at it, something 21.9%, and the nitroglycerin 29.1 percentage of nitroglycerin is used in this modified double base composite propellant, which act as a plasticizer. Beside this, triacetane is around 5.1 percentage, and which act as a solvent, and 2.5% of resorcinol is used as a stabilizer. And note that triacetane is basically is a trade name, and which is known as glyceryl triacetate. And this modified composite propellant can contain energetic nitramine like HMX or the RDX or any other thing. For obtaining a little bit more performance, also the higher density, but keep in mind that it also reduces the smoke generated during the combustion of this propellant. And a high energy composite solid propellant with aluminum powder can be designed by replacing the binder or elastometer, and if the grain is produced by casting, it is known as elastomeric modified cast double base propellant, and whose ISP will be ranging around something 270 to 275, which is a little bit higher higher than the conventional composite propellant. Unfortunately, it is being developed, but it is not yet to be used in practice due to certain limitation. And let us look at how we can manufacture the composite propellant. We had seen how to manufacture the double base propellant, which is quite involved in that, but the similar procedure we can think of. Generally, the oxidizer crystals are grinded into powder, that is the first step one can think of, and then the two different particle sizes, namely coarse around less than 300 micron, fine 30 microns, are used for better density of packing, so that it can fill the things, because of fact that higher value of solid density is desirable to have a compact propellant, as I had discussed earlier. And if the propellant has a high solid loadings and small particle, it will have a high solid surface area. Hence, it is difficult to mix and keep the solids weight. So, therefore, two ranges are being used, so that this problem can be avoided. And the other solid ingredients like catalyst, bonding agents, burning rate modifiers are added to this oxidizer, and then this liquid binder is mixed with liquid curing agents, and cross linkers and plasticizer, stabilizer, bonding agents that are together mixed. And then the ingredients of propellant must be mixed with the good uniformity and maintaining a wetting of the solid, so that it can flow into mold easily, because the flowability is very important for a better casting. So, therefore, it is important to maintain that, and the solid and liquid are mixed properly to produce a viscous slurry, but if the viscosity is too high, then also it will be problematic for flowability of the slurry. So, then the viscous slurry are poured into preformed mold or the die or to the casing itself, and must be cured between 60 to 150 degrees Celsius by the method of chemical methods, by using chemical or thermal method to form a tough rubbery mass, so that it can take the load, impact load, and also the shape of the grain is retained during the combustion process. If you look at these are the cross section of a typical composite propellant. You look at, this is your coarse oxidizer particle, and these are the fine oxidizer particle, like let us say if it is something around 30 micron meter, and this will be something around maybe 3 micron meter. And beside this, these are the binder which is on which all these particles are embedded. That means, the binder is making them to retain its physical shape and size. So, therefore, binder plays a very important role for binding all the particles. It is like the culture which bind the people together in a country. So, that is the things what affects. So, it is very important, and we call the culture is the soul of a country. Similarly, binder is the soul of a composite propellant, and it will act as also fuel. So, it is a very important thing we should keep in mind. Let us look at theoretical performance of STPV based composite propellant. If you look at STPV, is basically a translucent liquid, and whose color is like of a wax, and it is being used. Therefore, earlier days people are not allowing the carry the water even in the aircraft cabin. And let us look at the STPV based composite propellant of various kinds of oxidizer, like ammonium nitrate, potassium perchlorate, potassium nitrate, RDX, HMX, and at the chamber pressure of 68 atmospheric, and which is expanded to 1 atmosphere pressure. And you can see that the specific impulse is shown on the vertical axis, percentage of oxidizer is shown here in the horizontal axis. You can see that interestingly the AP, a peak values of thing is occurring around something 90%, and of course, the ammonium nitrate will be occurring something around maybe 95%, and this also peak is around 90%, and the other peak, the potassium perchlorate, is around let us say 85 kind of thing, is all are occurring maximum something 85 to 95%, is quite high. And then however, the RDX and MHA is having 100%, like the peak specific impulse for RDX and HMX occurs around 100%, which is quite high, because of fact that RDX and HMX will be having the stoichiometric ratio very proper, will be occurring at only at the 100%. So, therefore, you get a higher temperature, therefore, you get the higher specific impulse. But keep in mind that this other oxidizer, it is something around 90, but it cannot be really used in practice, because of fact that you need to have a flowability or the for casting. So, therefore, people go for something around lower percentage of oxidizer, even though you may get landing in specific lower specific impulse. Question arises why, and you will getting the peak values around something 90% for AP and around 85 to 95% for others. So, because of fact that The flame temperature is occurring at little higher percentage of oxidizer for AP if you look at here, and whereas the for HMX RDX you will get a big temperature here. Beside this, the molecular weight which will be playing a role, that also you can see it is occurring at a very higher percentage of oxidation. That is the reason why you will be getting the peak specific impulse at a higher percentage of oxidizer. However, in practice lower percentage of oxidizer is being used, so that it can be casted well, and then with the help putting some flowability and binders. So, let us look at theoretical performance of STP based composite propellants, and this dashed line is corresponding to AP composite modified double base propellant. You can see this ISP is basically its peak is occurring here somewhere around 50% or little bit more than that, and which is corresponding to the peak temperature here. And whereas for RDX CMD it is occurring at the 100% of the RDX, as I told that it is basically stoichiometrically well balanced at the 100%. So, therefore, it is occurring, but however, in practice it is not being used, and keep in mind that this theoretical performance corresponding to chamber pressure of 7 megapascal. Let us look at the product calculated combustion product composite propellant with varying amounts of AP and RDX. You can see here that the water content in this plot you can see is very high, and so also the oxygen concentration is very high when the AP concentration is beyond maybe something around 90% or around 90%. So, therefore, that really corrode the nozzles, and it may which enhances the erosion rate of carbon containing nozzles. Though another thing you can observe that SCl, that is hydrochloric acid, and which is varies from around 10% to the 20% in this, but for practical propellant it seldom exceeds the 14%. Therefore, higher percentage of ammonium perchlorate concentration should not be used for designing the propellant. And let us look at other constituents, particularly when the RDX concentration is being added to this composite. You can see very interestingly that this carbon monoxide gas and hydrogen is very higher, beyond it is 85% is having a peak values here. Because of fact that RDX contains relatively few oxidizing radicals, and binders surrounding the nitramine cannot really be fully oxidized. Therefore, you need to use little more percentage of RDX, and the product gases, as I told, are rich in hydrogen and carbon monoxide, hence the lower molecular weight. However, it cools the gases to a lower temperature, that is the disadvantage with that. And but interestingly, you can see the carbon content is receding when the RDX concentration is increasing, at least theoretically, and then as a result the smoke is getting reduced when you add RDX. So, therefore, from this you can know that how to design this composite propellant and what will be percentage by just carrying out a theoretical calculation. Of course, in practice it may be differed, but however, the trend will remaining same. So, let us look at certain data of the specific impulse of various kinds of the solid composite propellants and also combined modified cast double base propellant, and the burning rate is shown here. You can see that three kinds of there. One is the minimum smoke, this correspond to dashed line, and reduced smoke, and there is a thin line, and then solid line is aluminized. You can see that this is your CDB cast double base propellant, which is in this range is coming, and this is EDB extruded double base composite propellant, which is quite a wider range, around something maybe 7 mm per second of burning rate. to the around something maybe around 40 or 37, 38. And this CMDV, that is basically composite modified double plus HMX, when you add, is also the range is quite high, but not only that, it enhances the specific impulse. And of course, the elastomeric modified cast double base propellant will having a very high specific impulse, but its range of burning rate is quite low. And when you reduce the smoke composites, and basically you can reduce the smoke from a composite propellant by reducing the aluminum percentage or adding the RDX or combination of both. So, that is it is having a higher specific impulse, but it is also quite a wide range of burning rate. And reduce smoke, you can have EMCDV, that is elastomeric modified cast double base propellant plus AP, and composite propellant, of course, you can use AP, aluminum, polymer, all those things. It is having a higher specific impulse, having a very wide range of the burning rate, that is a good. Of course, high energetic even can have. So, you can see that the various kinds of composite propellant we have seen, and it is having a wider range. You can go on experimenting and finding out better propellants and combining all the double base and composite, and by using the innovative methods, and then there is a lot of more can be done, and we can see as we go along about their characteristics of how to calculate burning rates and other things. And with this we will stop over. In the next lecture we will be discussing about liquid propellant and types of liquid propellants and also their characteristics. Thank you very much.